When you look up at the night sky, you see a universe that feels alive with light. Galaxies clumped together in magnificent cosmic webs, stretching across billions of light years. This is the universe we think we know, a place of brilliant structure, where matter has gathered into great cities of stars. It's a universe defined by what's there. But what if I told you there's a place in our universe so vast and so empty, it's nicknamed the Great Nothing, a void 330 million light-years across, where thousands of galaxies are simply missing. It's a hole in the fabric of the cosmos, an absence so profound it pushes the boundaries of our cosmic map. For decades, astronomers believed this colossal emptiness was just that, empty, a statistical fluke maybe, but ultimately, a barren desert in the cosmic landscape. They were wrong. Astronomers expected to find almost nothing there. But what they discovered hiding inside this abyss is something that seems like it shouldn't exist, a strange tube-shaped string of galaxies that presents a fascinating cosmic puzzle. This structure isn't just a random scattering of survivors in a desolate wasteland. It's an organized, coherent feature in a place where organization seems unlikely. It's a clue that points to a cosmic history we're only now beginning to understand. Today, we journey into the heart of the Boötes Void, to the loneliest galaxies in the cosmos, to ask a simple question: how did they get there? And what sculpted them into a shape that tests our most fundamental theories? To get why the Boötes Void is such a mind-bender, we first need to understand what the universe is supposed to look like. Our modern picture of the cosmos is one of intricate, breathtaking structure, but it all started from near-perfect uniformity. In the first moments after the Big Bang, the universe was an incredibly hot, dense soup of particles and energy, expanding at a ridiculous rate. On the largest scales, this soup was almost perfectly smooth. Almost. That one word, almost, is the key to all cosmic structure. Down at the subatomic level, the primordial energy of the universe was alive with tiny, random quantum fluctuations. Think of them as impossibly small ripples in the fabric of reality. As the universe expanded, these microscopic ripples were stretched to astronomical scales. A region that was, by pure chance, a tiny bit denser than its surroundings became a gravitational seed. Over hundreds of millions of years, gravity got to work. These slightly denser regions pulled in matter from the slightly less dense regions around them. The rich got richer, and the poor got poorer. But it wasn't just ordinary matter doing the pulling. Most of the matter in our universe is invisible dark matter, and it formed a massive, unseen scaffolding first. Ordinary gas and dust then fell into these dark matter halos, eventually cooling, condensing, and lighting up as the first stars and galaxies. Over billions of years, a magnificent pattern emerged, the cosmic web. Think of it like a sponge, or maybe a neuron. The matter in the universe isn't scattered randomly, it's organized. There are unimaginably long, thread-like structures called filaments, which are basically rivers of galaxies. Where these filaments cross, they form dense, brilliant knots called galaxy clusters, the great metropolitan hubs of the cosmos. And in between all of this amazing structure, emptiness. These are the cosmic voids, vast, underdense regions that have been cleared out as matter gets pulled away to build the filaments and clusters. They are the bubbles in the cosmic foam. This whole structure, the web of filaments, clusters, and voids, isn't just a neat theory. It's a direct prediction of our standard model of cosmology, and it's exactly what we see with massive galaxy surveys. So, according to the blueprint, voids are a natural, expected part of the universe's architecture. But the blueprint has its limits, and the Boötes Void stretches those limits to the breaking point. The story of the Boötes Void kicks off in 1981 with a team of astronomers led by Robert Kirshner. Their goal was ambitious, but simple: create a three-dimensional map of the universe. Back in the 80s, this was painstaking work. Looking at the sky gives you a 2D picture. To get the third dimension, depth, you need to measure a galaxy's redshift. As the universe expands, distant galaxies are carried away from us, and their light gets stretched to redder wavelengths. The bigger the redshift, the farther away the galaxy. By measuring the redshifts of galaxies in a specific patch of the sky, the team hoped to reveal the universe's large-scale structure. They pointed their telescopes toward the constellation Boötes, the herdsman, and started measuring. They expected to find a steady succession of galaxies, but as the data rolled in, a deeply unsettling pattern emerged, or rather, a lack of one. They kept finding nothing, an enormous gap. Where their models predicted a steady march of galaxies into the distance, there was only a profound cosmic silence. The team's first reaction was disbelief. Surely the equipment was broken. A software bug? The idea of a region of space this empty was so far outside the accepted theories that a technical glitch just seemed more likely. They checked their instruments, recalibrated everything, and ran the observations again. The result was the same. They had stumbled upon a void of unprecedented scale. The final discovery was staggering. They had found a roughly spherical region of space, about 330 million light-years in diameter. To put that in perspective, our own Milky Way galaxy is about 100,000 light-years across. You could line up 300 Milky Ways, end to end, just to cross the Boötes Void. Based on the average density of galaxies, a space this large should contain a few thousand galaxies. The initial survey found just a handful. Later, more sensitive surveys have only bumped that number up to about 60. That's like flying over North America at night, expecting to see a carpet of city lights, and instead finding only a few dozen scattered street lamps in an entire continent of darkness. Here's a fun thought experiment that captures the sheer isolation. If the Milky Way were located near the center of the Boötes Void, we likely wouldn't have known other galaxies existed until the 1960s. For most of human history, our night sky would have been completely empty of other galaxies. We would have thought we were utterly alone. It's an emptiness so complete it could hide the rest of the universe from view. We're standing at the edge of this cosmic abyss, but the even bigger mystery is what lies inside. The emptiness itself is baffling, but what astronomers found hiding in the dark is what really changes the game. If you're enjoying this journey to the weirdest corners of the cosmos, take a second to subscribe. You'll be supporting our deep dives into the frontiers of science. And trust me, we have so much more of the universe to explore together. Now, let's step into the void. For years, the main puzzle of the Boötes Void was its size. But as technology improved, a new, far more perplexing mystery came into focus. The few galaxies that do exist inside the void aren't just scattered about randomly. They're arranged in a distinct and peculiar pattern. Later surveys revealed that the 60 or so known galaxies are concentrated in a narrow, tube-like structure running roughly through the void's center. This isn't just a subtle alignment, it's a coherent feature. Imagine a vast, dark sphere the size of a small country, and suspended in its center is a single, glowing string of pearls. That's essentially what astronomers found, a filament of galaxies where no filament should be. This discovery turned the problem on its head. Any galaxies left inside a void should be lonely relics, drifting aimlessly. The presence of an organized structure suggests something else, a shared history or a formation process that sculpted these galaxies into a shape that defies a simple explanation. So, how do you explain this? How do you create a giant bubble of nothing and leave a string of galaxies in its heart? The leading hypothesis is known as the coalescence model. The idea is that the Boötes Void isn't one single primordial whole, but is actually the result of many smaller voids merging over cosmic time, like soap bubbles in a sink. As the universe evolved, smaller voids expanded and merged, pushing matter into the walls and filaments between them. This model also offers a potential explanation for that mysterious tube of galaxies. When bubbles merge, the film that once separated them is often the last part to go. In the same way, when smaller voids merged, the wall or filament of galaxies that lay on their boundary might have been squeezed together. So, the tube of galaxies could be the last surviving remnant of the boundary between the original, smaller voids that created the Great Nothing. It's like a gravitational fossil, the seam left behind after stitching together vast patches of empty space. This is a plausible picture, and it's consistent with our standard cosmological model known as lambda CDM. However, getting simulations to produce such a clean, isolated structure inside a void of this size is challenging, making it an active area of research. The anomaly in the abyss remains a fascinating puzzle. The Boötes Void and its strange central filament are more than just a cosmic oddity. They're a gateway to some of the biggest questions in science, forcing us to test the limits of our standard cosmological model. And remarkably, studying this distant emptiness might connect to a major puzzle closer to home, a crisis in cosmology known as the Hubble tension. The Hubble tension is one of the hottest debates in physics today. It's a fundamental disagreement between two different ways of measuring the expansion rate of the universe. When astronomers measure the expansion rate using relatively nearby objects, they get one value, about 73 kilometers per second per megaparsec. But when they measure it based on the light left over from the Big Bang, they get a different, slower value, about 67 kilometers per second per megaparsec. The measurements are now so precise that this isn't a small error, it's a major discrepancy that suggests we're missing something. For years, scientists have proposed exotic new physics to solve this. But what if part of the answer isn't new physics, but our cosmic address? Some recent research has explored a compelling hypothesis. What if our own Milky Way is located within a large, underdense region of space, a local void? If we are inside a void, the denser regions surrounding us would exert a stronger gravitational pull, creating an outflow of matter away from us. This could make local galaxies appear to be receding faster than the true cosmic average, potentially explaining the Hubble tension without rewriting the laws of physics. While this idea is still debated and has its own challenges, it shows why understanding voids is so important. This brings us back to Boötes. It's the most extreme and perfect laboratory we have for studying these environments. By observing how its structure evolved and how gravity and dark energy interact within it, we can test the very models being used to tackle the Hubble tension. The Boötes Void is part of a larger conversation about huge structures in the universe that seem statistically rare. While these too big to exist structures are fascinating, the current consensus is that our standard lambda CDM model is still the best framework we have. They don't break the model, but they certainly stress test it. Of course, with any great cosmic mystery, you get some wild speculation. Some have wondered if the Boötes Void is the work of a hyper-advanced alien civilization that harnessed the energy of thousands of galaxies. It's a fun thought experiment, but there is zero evidence for it. The simplest explanation that fits the data is usually the best one, and right now, the evidence points toward natural cosmic evolution, not galactic super-engineers. Our journey took us from the familiar starry night sky to the edge of the loneliest expanse we've ever found. We traveled across 330 million light-years of near-total emptiness, a place where thousands of galaxies are missing from the cosmic census, and in its heart, we found its central puzzle, a strange tube of galaxies, a structure organized in a way we're still working to fully explain. We've explored the leading theory that this supervoid formed from smaller voids merging like bubbles, leaving behind a fossilized filament of galaxies. It's a compelling idea, one that fits within our standard model of the universe, even if it pushes it to its limits. This is the real beauty of science. Discoveries like this aren't failures, they are signposts. The Boötes Void, once just a curiosity, is now a crucial natural laboratory. In its emptiness, the effects of dark energy, the force driving our universe's expansion, are laid bare. Studying these voids might be one of the best ways to understand the force that will dictate the ultimate fate of our cosmos. And the possibility that we might live in a similar void makes understanding Boötes essential to understanding our own place in the universe. The discovery of the Boötes Void in 1981 fundamentally changed our view of the cosmos. It showed us that the universe is a complex, foam-like architecture of brilliant filaments and deep, dark voids. It taught us that the universe is defined as much by its absences as by its presences. Today, that discovery continues to ripple outwards, challenging us to refine our best theories. The great nothing is not empty. It's filled with questions. And as we keep looking, it will surely be filled with answers we can't yet imagine.